We're going to continue with some connectedness notions. The things on this page were covered in video 311, so they're here if you want to pause and review them before we go on, but I'm going to go ahead and scroll down and continue on. There's a notion of connectedness, what it means there. Again, if you want to pause and read that, you may. Theorem 1 there. But what I want to do is continue on with this with some key features of connected graphs. The first thing being a cut vertex of a connected graph is a vertex so that when you remove that vertex and all the incident edges on it, then what you get is disconnected. And a bridge is similar, except it's an edge, so that if we remove the edge, it's an edge of a connected graph, which when removed results in a disconnected graph. So you don't remove any vertices when you remove the bridge, but you can see below what we have here, the cut vertices would be, well, let's just see, what would be a cut vertex? Well, if you remove H, then that would mean that J would be left alone, because you would remove those edges right there. So that would be H is certainly a cut vertex. In like fashion, if you remove B, then you'd have to remove, let me go ahead and get rid of some of these other things that we have there. You'd have to get rid of certain edges as well. You'd have to get rid of this edge here and that edge there and that edge there, and it would result in a disconnected graph. And in like fashion, C is one, so we'd have B and C, but none of the others are cut vertices. If you remove J and its edge, the graph is still connected. So those are the cut vertices. The bridges, well, in this case there are two bridges. So let me get rid of these green marks here if I can to go back and look at this. So the two bridges, first of all, BC is a bridge, because if you remove it, then you've disconnected the graph. Everything else would remain, so that's disconnected, so that's one. And the other one that is HJ, because if you remove it, you've got J standing there isolated after the fact. So the bridges are BC, that's an edge, so I use the braces to indicate that undirected edge, and HJ likewise is a bridge. But there are no other bridges here. Anything else that you might remove would still retain a connected graph. Okay, let's go down here and talk about some directed graphs and their relationship to connectedness. So we say that a digraph is strongly connected if for each pair of distinct vertices, U and V, there is a directed walk from U to V. Now that has to be for each pair, U and V, so that means V to U would also have to have that walk from V to U as well as there is one from U to V. Right? It doesn't say there's a directed walk from one of them to the other. It has to go, there has to be one from each to the other. Okay, from each vertex U to each vertex V, there is a directed walk. It's weakly connected if when you take away all the directedness of the edges, you get the underlying digraph and it's connected. So we'll look at this one down here. This one, this graph is not strongly connected because there is no directed walk from any vertex to D. So for example, we've said, is there a directed walk from E to D? There is not. We could get to C, but once we're at C, there's no way we can go from C to D. So there's no directed walk from E to D. For example, there's plenty of other ones here for which there's no directed walk. There's no directed walk from A to J. There's no way to get from A to J. If you look on the graph, you cannot do it directly. If you come over here, you still can't get in. you come over here, you still can't get in here from A. If you go from A to E, you can't get into the inside. If you go from A to E to C, you can't get into the inside. If you go from A to C to B, you can't get in to the inside. So there's no way to go from A to J. So there's many examples of this. This is just one example of a failure to have a directed walk from one of the vertices to another one. So the issue in this case is what are the biggest strongly connected pieces, and those are the strongly connected components. So I'll try to identify those here. So we'll take a strongly connected subgraph and take the largest of these, and those will be the components. You might be able to see at a glance that the outside here, all of this is connected, but it's not connected to anything else because of the direction of the arrows on the graph. I really did intend for this one to go out, and I will just add that now. So none of the outside ones are connected to any of the others, and so that is a component. So here's the components, a strongly connected components would be, first of all, the vertex set would be A, B, C, E. Notice they don't connect to D either, so D is not a part of that. And that's the vertex set for it. Edges would be, these are directed edges, so I'll write them as ordered pairs. A goes to E, E goes to C, C goes to B, and B goes to A. So that would be the edge set for this subgraph that's connected. This, and the first part there that I wrote down, there's the vertex set right there, and this is the edge set for that subgraph that I've sketched right there. So it does look just like what I've got drawn there, up there. There's the strongly connected component, where that's A, whoops, wrong direction. This is B, this is C, and that's E. Right, so what are the other strongly directed components? Well, the inner circle works as well. Also, so that's one of them. A second one would be, the vertex set would be GHI, or let's do FGHI just in order. FGHI. And the edge set for this one would be the set where we go F to G, G to H, H to I, and I to F. And is that everything? Can we go any bigger than that? No. We can go in to J from H, but we can't get back out. So if we add a J, that is not strongly connected to the rest of them. So we get that other inner circle going the other direction with vertices G, here F, H, and I. And that's not connected to any of the other piece. So that's a separate one. And then finally, we're left with two isolated ones, J by itself as the vertex set, and E is the empty set, because it's not connected to any others. It is given a name. It is called a sink, because everything points into it there. Whereas D, the last one, whoops, sorry. The vertex set is D, singleton, and the edge set in the last one is also empty. So the last component is just this isolated vertex here. Notice that we haven't used all the edges in these strongly connected components, and you won't generally be able to. But D itself, that singleton set, is strongly connected by itself, and it is called a source because all of the edges incident on D are pointed out from D. Like if you think of the arrows indicating water flowing, then that's like a spring. It's a source. Whereas the sink at J is like the drain. Everything's flowing into that one right there. So there's some concepts on connectedness that go beyond ways that graphs can be easily disconnected with cut edge or a bridge, and then connectedness in a directed graph. And in the next video I'll talk something about these special kinds of circuits, Euler and Hamiltonian circuits.